All right, so we're going to talk about chi-squared, and you can sit and read this paper and go through it and all that kind of stuff, but I'm going to kind of summarize what the idea is of a goodness of fit test or a chi-squared test. So chi-squared is written as like x squared. You're not actually squaring anything at the end. So we're doing this goodness of fit test, and we're trying to see if our package of M&Ms in this case is the same as what the M&M website says. So they say for a plain package of M&Ms that they make it in these percentages that you can see right here. But we're going to see if that's actually true or not based off of our sample of our plain M&M package. Okay, so we're going to be calculating a statistical value called a chi-squared, and then we're going to use a table that's on our equation sheet to determine if that's actually the case or not. So first we have to state our null hypothesis. And so a null hypothesis is the prediction that something is not present, that a treatment will have no effect. There's no difference between the treatment and the control. It's null. There's nothing. You kind of have to think of it that way. A lot of times we're actually going to reject our null hypothesis and say there is something that happened. But sometimes we're not. So our null hypothesis is there is no significant difference between what we counted in our package and what the Mars company stated for this case, okay? Our alternative hypothesis is there is something different between what we counted and what the Mars company stated. And so we need to calculate a chi-square test, this is the equation for it. It's the sum, that's what that little weird backwards E is, of our observed number minus our expected number squared divided by our expected number. So the observed is our actual count, what we actually observed, and the expected is what they said, okay? So let's pretend we actually counted some M&Ms. I totally made up these numbers, friends. And so what we're going to do, we observed 10 brown M&Ms, 4 blue, 6 green, 3 red, 8 yellow, 7 orange for a total of 38. And then in order to calculate my expected, I'm going to take, if I scroll back up, it says 13% are brown. So I'm going to say 13% of my total, so 0.13 of 38 is my expected number. And I'm going to kind of go through one of these calculations here. So I get I'm going to erase that as I go. So 4.94. So you can see that that's a difference. You might be like, oh, 10 to 4.94, that's a big difference. Is it significantly different? That's what our statistic is going to find out. So then, now I'm just going to go down. I'm going to do the difference between those. So I do observed minus expected, and I get 5.06, and then I'm going to square that number, and I get 25, and then I'm going to divide it again by my expected. That's the equation. So this is, and I get 5.18. Okay, then I'm going to do that for each of mine. So I'm going to go back up, and I'm going to get my blue number, and my blue is 24%. I don't feel like that's the right number. And just in my head. And so I do 0.24 times my total, and I get a number, and then I'm going to subtract those numbers. I'm going to square it, so negatives won't matter in our difference category, and then I'm going to divide it by expected. Once I have a bunch of numbers here, so I'm just going to literally just make up some numbers just for funsies here. Then I'm going to get some kind of total. So 13, 15, 16. So I get 21 is going to be my total. Okay, so I just added all the numbers up in this column. It's the sum of the difference squared divided by the expected. That's my chi-squared value. Okay, so that right there is my chi-squared value. The other number I need to know is my degrees of freedom. It's the number of color categories minus 1. So I had 1, 2, 3, 4, 5, 6 categories minus 1. My degrees of freedom is 5. Now, on my equation sheet that you get on every single test and we have in the classroom, and or you can just literally Google AP Bio equation sheet, you find a chi-squared value. And you're going to find where it says P equals 0.05 on your equation sheet. And there's going to be a number on there. That number is what we call the critical value. And that's what we're going to compare to. And so what we're going to say is at 5 degrees of freedom, We calculated that. The critical value for p equals 0.05 is 11.07. I got that off the chart off my equation sheet. The chi-squared value for this experiment is 21. Therefore, I'm actually going to reject my null hypothesis. There is a difference between what I observe and what I expected. So if my critical value is smaller than my chi-squared value, then I'm going to reject my null hypothesis. So if, let's just write that out. So if chi-squared is greater than critical value, you reject the null. And if my chi-squared is less than my critical value, meaning there's very little differences, then I will accept my null. And all the differences that I see between what I observed and what I expected is just by random chance, okay? And then I go and explain why there is a difference. So if I'm writing this in a reasoning section, I have to explain why there is a difference and why not. And so then this whole purpose is done to better support my argument. It's better to support my reasoning, because my reasoning is, how does my evidence support my claim? So this is making my evidence more solid and more scientific. Okay, and then just for our woolly worms, so for our woolly worms, when we did those, we found our expected a little different. In that case, we expect to pick up all the colors evenly. Or there is no natural selection. That would be our null hypothesis. So expected numbers are really just is the same for every single category. And it's really just the average, because you'd expect to pick them up all evenly. Okay, so then you can go ahead and calculate a woolly worm number and then use that to help support your evidence of, is there natural selection occurring or not as we were predators.